Hello, good afternoon. So this is group two. We are working on swarm intelligence with our focus being on the ant colony optimization. So what is the ant colony optimization? So the ant colony optimization is a type of swarm intelligence that actually uses a natural phenomenon, right? The fact that ants are able to find their source of food and then able to trace back to their homes and able to communicate with other ants as well to actually track the source of their food. And this all happen with a dropping or an expulsion of a type of chemical called pheromone, right? So that is what the ant optimization colony is basically based upon. And the fact that these ants are able to use the shortest path or the shortest route to their food source, right? So this is the code that we have used. So we use a paper, and the paper is actually using the same ant colony optimization together with another idea that they call the fuzzy axe, right? So I'm dropping in the paper here quickly before we jump onto the code. So the paper is over here, which is titled A Novel Ant Colony Algorithm for Solving Shortest Path Problems with Fuzzy Arc Weight. So it's just another improvement on top of the ant colony optimization. So the improvement here is actually the fuzzy arc weight. Perfect. Now let's jump onto the code and its implementation. So over here, the implementation was fully done with Python using Python's framework called Flask. Here we have all the necessary import that has been done, and then we instantiated our Flask application. Then we have a class of ant. So this ant is just a class that will be instantiated. We're going to instantiate from this class using each of the ants objects within the ant population. So inside of it, we have the node that we are to add. So basically, what we are trying to find here is we want to find the shortest route while leveraging fuzzy arc weight. So fuzzy arc weight means we're just introducing some level of entropy or some level of randomness so that we are not dealing with the same path, but we're having varying path, right? So we have a function that we are using to add node to the path, right? So we have a path, and the path is going to be a matrix. Then we are going to be appending each of the node to the path. We also have a function that will be able to calculate the distance from the source to the destination. So in other words, moving from moving from source A to source B will be a path. So we have to calculate for that distance so that at the end of the day, we can find the optimal distance. Now we have another function outside which we call choose the next node. So choose the next node function is actually a function that will take in the graph. The graph is that's basically the all the paths that are possible for the ants to travel to find the food. We have the pheromone matrix. So the pheromone matrix is actually a matrix that is used to change the chemical composition of each path because we don't want the algorithm to be skewed, right? We have the current node, so we need to track the current node where the ant is, and also know the visited node where the ant is has already visited, right? And also we have the pheromone exponential weight. So this is also a varying number that we actually use so that together with what we call the pheromone evaporation rate, we can vary the pheromone chemical level with time. So we're not going to have the same pheromone level that will be on the same path forever, but it is going to be what to be decaying from time from the day that it was actually instantiated or created. Now, before we can choose a next node, what we need to do is that we need to actually look through all the graph, all the paths, and check if we have visited that node, right? If we haven't visited that node, then we can then proceed to visit the node. But if we have visited it, then we are going to vary the pheromone matrix. So as I said, this pheromone matrix is actually going to be the exponential of the exponential. Sorry, it's going to be the exponential of the pheromone itself. That's the pheromone weight, such that with time it will decay. Now, if they have not visited that, then we're now going to create a probability, right, for the ant to visit the other paths, right? We need to find a probability that if we have five paths, the probability of the ant visiting any of those five parts will be based on the percentage or the concentration of the pheromone chemical, basically. Now we move down to find the another function that will update the pheromone matrix, right? So we're basically just telling, we're taking all of the ants within the population. So, right, for each of the ants, basically, for each of the ants that is going to take a path, we are going to drop a pheromone evaporation rate on each of the paths. So if an ant takes path A, the pheromone matrix of path A is going to drop, right? So that when ant B is coming to take the same path A that ant A took, it will realize that if the pheromone 10 is going to reduce to 9. So that is what we need to do. So with time, we have a constant evaporation rate where over a period of time, there will not be any more pheromone chemical on the path. So that way, it could help the ants to take a new path, especially when the food that they were trying to track down has finished, right? So they are going to take a different path, right? Now we have the real function, which is the ant colony optimization. So it's going to take the entire um, geographical area or in the entire metrics, right? We're going to have the number of ants, that's the population of the ants. We're going to have the maximum number of iterations. I mean, you don't want this particular function to run forever and ever. You need to like clock it at a certain rate so it doesn't run forever. We have the initial pheromone, that's the initial chemical concentration we are going to drop. We have the pheromone exponential weight, then we have the pheromone evaporation rate, as I said, along, and the number of nodes that you want to explore. So number of nodes basically is all going to be the number of the paths that is going to be explored, right? Now we're now going to find the best distance. So we're looking for two things: best distance and then the best path, right? Now we now iterate over the number of iterations that is going to pass to this function. So we're going to do that from our UI, or we can do that from our CLI. Now we iterate the number of maximum number of iterations, and then we use an ant over the total number of ants that is going to be passed, right? So we're going to iterate over a total number of what? The population, right? Then we try to find out if the length. So we're now trying to set a path is it visited. If a path visited is less than the number of nodes, it means that the current we are now going to set the current node to be the last path, right? Because we are trying to explore all the nodes. That's basically what we're doing over here. Then we can now let's calculate the distance using the graph, right? And also if the distance that being traveled by the ant is less than the best distance, it means that the distance that the ant just traveled is actually the optimal path. Then we set that path to be that particular distance traveled by the ant, right? Now we just create a list of the best path and just iterate through all the paths and then append them together, and then we return those two. Now the last piece of the function has to do with the generate the random graph. So as I said, we could do this with a static path, right? So static path as in like we could create a matrix where moving from point A to point B will just be 10, from B to C will be 15, right? But the point is that we're trying to have a concept, we're trying to vary, we're trying to increase some entropy or some randomness such that we are not actually making the path fix. Because if we run this against this matrix, it means this matrix will never change, right? It means over time you're going to be getting the same results and the same results over and over again. But now that's now where the fuzziness come in. So we have the function that takes in the fuzziness, so that is a value. Then we now use this fuzziness, right, and then creates an array of and create a matrix using NumPy whereby we introduce this fuzziness inside the graph, right? So it means that anytime this function runs, we're going to generate different set of values. So that's the kind of entropy we're trying to introduce in here. Now, we're going to run this. After that, we then move into how this operates on a UI form. So um, we move this, and then we can now run Flask up. Yes. Right? So we have a UI in a template form. So we're actually going to, these are the key things. We're going to make a post request just to see them from the UI form. And that post request will have the population size of the ant, the maximum iteration, the initial pheromone exponential weight, the pheromone is evaporation rate, now the fuzziness, which is going to be a number that will be varied, the number of nodes, right? And then basically we then generate the graph or the paths that are going to explore. Then we print out the best path and the best distance as well. And then we render all this information back onto the template called index.html. Now we go to 302 on our browser. Let's see. Sorry, chapter 3002. Okay. So now we have pre-populated values for the beginning. So we have a population size of five. That's five ant. We have a maximum iteration of 100. We have initial freedom of one. We have exponential weight, evaporation rate, number of nodes, and fuzziness. Then we're going to run it, right? So when we run it, we realize that we have a best distance offered as that is 74.86. Now, if we go back to our terminal, we realize that we're getting the same best distance, 74.86. Then we have the best path, right? So what the best path simply means is that because we are not actually we are making this random, it means that if we were to move from point A to point B, right? That is, it could be like moving from 0 to 2, then move to 2 to 1, then move 1 to 3. That's just basically what is now showing over here for us. And then we can then vary this fuzziness probably and put another volume of 5, run again, then we have another distance of 131, right? So that'll be 131.184, and then that will generate a different path for us, which means you have to move from path 2 to 0, then move from 0 to 1, then move from 1 to 3. And let's have one more run again by just changing the fuzziness to 6. Then we have 63, right? So we have 63, that's the best distance, 0.44. Then it means the path for us to move is from 3 to 2, 2 to 0, and then 0 to 1, right? That will be the optimal path that you have to take. So that is it for us on demonstrating ant colony optimization using fuzzy arc weight. Thank you and see you later.